going to start off with the basic product presentation. It actually depicts why system level design is required and what kind of application areas we are targeting at. And then I'm going to bring up few demo examples as well that shows you how exactly you will be conducting architecture exploration, power and performance analysis of system designs. Okay, so for today's session we are going to keep it as very simple. So once we are good at it at this point, then we can go ahead with kind of little more complex things as well. Okay.
Okay.
Yeah. So you can see my screen, is it?
Yes, yes.
Okay, great. So I'm going to start off with a basic introduction to Mirabilis Design. Mirabilis Design is a Sunnyvale, California-based company that provides software solution for architecture exploration, power and performance analysis of your designs early in the design flow. Before writing an RTL code or before going to implementation of your designs, you will actually model your specifications or the concepts in VisualSim Architect, considering both hardware as well as software, and run simulations to see whether you are meeting the requirements or not. Requirements with respect to throughput, utilization, latency, and all the performance level characteristics, whatever it is there. Once you are satisfied with the configuration and the requirements, whether you have met or not, then you will be passing these specifications to the design teams to proceed further to the next stages. The main reason for providing this kind of solutions is that we have identified about more than 60% of every project work is mainly involved with respect to selecting the hardware architecture, selecting the architecture of your design itself. Rest of the system is very easy because you know that what you're going to do. If you don't know what you're going to do, then actually problems occur, and there VisualSim comes into picture and helps you in identifying the hardware architecture as well as the software architecture to see whether you are meeting the requirement for the set of applications that you're going to run on that. Okay. The major product from Mirabilis Design is VisualSim Architect, which is a completely graphical modeling and simulation tool. Okay. So, using VisualSim Architect, people will use these kind of software solutions to design and explore systems. Systems in the sense it is a complete system. It could be a complete aircraft, complete automotive system, or it could be a complete SOC, or even a software part of it as well. We are one of the biggest modeling IP providers, and we have more than 500 system level modeling IP library blocks that are embedded with timing and power details. Okay. So please stop me if I'm going very fast, or if you have any questions.
No, you can proceed. No
sure. Yeah. So when we talk about system level design, it is nothing but what you're going to build. A system is nothing but what you're going to build. It could be a satellite, it could be a wireless system, an automotive, or a semiconductor such as SOC itself, or kind of custom protocols you're developing. A networking system with you'll be having various nodes that are connected to voice over IP phones, or it could be a kind of AFDX based systems, things like that. So using VisualSim Architect, what we do is we enable you to model a system that is having multiple domains in it. Okay. For example, if you consider an automotive, for example, consider a car itself. Okay. Car has ECUs in it. ECUs are nothing but your semiconductors, right? You'll be doing some processing in it. And multiple ECUs are connected over a network, right? So we enable you to model network part of your system as well. You will be placing your ECUs across your car, and you can model such kind of scenarios as well. In networking, for example, in most of the modern cars, you'll be having some custom protocols to make sure that no one from the outside can hack that particular car and do some nonsense with it. So we can help. We help in modeling custom protocols in it as well. Hence, we call VisualSim Architect as a kind of heterogeneous modeling and simulation environment. In a single tool, you can model semiconductors, you can model a wireless system, you can model networking part, and you can model custom protocols like that. You don't have to go for different tools to actually have a complete view about your system itself. You can have everything in a single modeling and simulation environment. Okay?
Okay.
So then question arises, why do we need system level modeling? What is the requirement? Right? So if you look at any complex systems, one of the major characteristics that all complex systems possess is the resource limitations. Resource limitations in the sense of processing speed or communication bandwidth, or resource limitations with respect to contention for processing and communication resources, or even the resource limitation could be at the level of memory hierarchy and memory access times and storage width kind of things as well. Okay, and if it is a kind of handheld device, or if it is an avionic system, things like that, then you will definitely have to consider power consumption as well. Whether you have enough power for running your application for a span of time or something like that. Okay, so these are the kind of resource limitations we call it as, and we address these limitations and help people in overcoming these challenges as well. And also it is not specific to VisualSim, it is actually kind of generic with respect to all system level modeling methodologies. People will be identifying whether my processor is running at a desired rate, whether I'm getting my performance what I was expecting at, whether I'm running all the tasks without any rejection. Such kind of things are modeled and identified at the early stages of your design itself, so that you can address those issues at the later stages or even at the level of system level modeling and address those issues as well. Okay, so these challenges are actually major reason for your system interdependencies and kind of system unpredictability as well. So let us consider one scenario in which you can consider there is one system that is having two CPUs, one DSP core and an IO that are connected together using two buses and a bus bridge. Okay. So when you run only one application on this particular platform, you'll never see any contention for resources, right? Consider that the top one is actually the application which we are running on it, and if you break down your application into multiple parts, you'll be actually having one task that is actually going to your IO, and the task 2 is going to CPU 1, and task 3 is actually going to DSP. So in this case, there is no reason for any contention for resources at all, because there is only one application running on it and which is fully pipelined, right? So problem happens when is that when you run multiple applications on the same platform. For example, in this case, we have the second application which you can see at the bottom. We're actually running on the same platform. Okay, you can see here, IO has been accessed by two tasks now. Application 1 is also accessing IO, and also application 2 is also accessing IO. There could be kind of contention for accessing that particular device itself. If you consider the DSP core, it is again having two applications or two tasks that are running on that particular device. So there could be a kind of contention for resources. You may have to wait for some time before, for example, if the task 3 is having higher priority or which is running on DSP core, if this at the same time task 2 of application 2 arrives at the DSP core, you will have to wait for some time. So in that case, what happens is that there could be a kind of delay in processing the task 2 of application 2, so that you can't actually simply compute using a kind of formal methods, because the internal delay which is happening at DSP core is kind of out of control with respect to user. Okay, so in such scenarios, it is very difficult to go with any formal methods or kind of using spreadsheets to identify what is the throughput, what is the latency I'm going to get for my applications, which I'm going to run on that particular platform.
Yeah.
Right. For example, if you consider one image processing, or for example, if you consider your camera application itself in your mobile phone, when you open up your camera thing, it will actually take a picture and it will actually send the data to the GPU to process that particular image and send it across to the destination. Maybe it is sending to the memory, right? So you can consider that way. In that application itself, capturing one thing and sending the data to the GPU is the second task you can consider. And next, you're writing that particular image to the memory is the third task, right? So that's why. For example, at the same time, if you open up one more thing, for example, you're saving some data to the memory itself, right? So in that case, you may feel some difference with respect to the performance of your performance of your mobile. It may take few seconds more compared to the earlier times, right? So like when you run more and more application on your hardware architecture, there will be issues with respect to latencies, issues with respect to complete performance of your design. So you may have to allocate some time for processing of each applications or each tasks on your platform, or you may have to redirect how you're mapping your application onto the hardware architecture itself. Right? So these are the kind of challenges what typically system level designers will be having at. Okay. So now consider this as your version 1 of your system. Okay. So now you have provided some timing. You have allocated some time slots for running all these tasks on your hardware architecture, and you're running two applications on your platform. Consider this. This is your current version of your system. So later on, what happens is that you will have to. You may think that maybe after version 5 or version 6, you may have to run two more applications on this same hardware architecture. You don't want to change your hardware architecture, but you want to try out with running two more applications, right? So what happens in that scenario is that typically there are two approaches to it. One is that you will have to study a lot with respect to the hardware architecture to see whether I can run one more or two more applications on the same platform. Otherwise, you will have to over-engineer something in your hardware architecture. You will have to speed up something in your hardware architecture, speed up your processor speed, speed up your memory speed, or speed up your bus, something like that. Okay, so there are two approaches. One is that you have to study a lot with respect to hardware architecture. The second approach is over-engineering your design. So which is actually, the second approach is majorly used in many scenarios or many applications I can see, right? So if you consider the following graph, okay, so in this case, we have the system response time for two architecture. One is running at 200 megahertz, and the second architecture is running at 400 megahertz, which means we have over-engineered the design by running bus at 400 megahertz. It's about doubling the frequency, right? So in that case, you can obviously assume that when you double the frequency, you will actually expect half of the latency what you're getting at the initial stages. But if you notice over here, the red one is actually the system which is running at 200, and the blue one is actually running at 400 megahertz. At certain points, you can see here, the latency is actually higher compared to the bus which is running at 200 megahertz. Right, which is completely unpredictable and which is almost impossible to identify in any formal methods or using any other using spreadsheets or things like that. So this is a kind of bigger bottleneck we have seen with many of our customers. Reason could be one reason could be your memory access time is not is actually very slower compared to the I mean when you run more application, which is not good enough if you run two more application, or the buffer capacity what you have provided is not sufficient, or your processing speed may not be sufficient enough, or as I told earlier, when you run multiple applications, your DSP may not be ready to process all the data which is coming in. Maybe all the data which is coming in is in queue itself. It is not processed out, right? So those are the kind of bottlenecks will arrive when you run, when you over-engineer the design and try to run more and more application on the same platform.
Okay.
So using this approach, you can identify where exactly the problem is and what exactly is happening at your system when you play around with your parameters or configuration of your systems as well.
Okay.
Any questions?
Okay. No question.
Okay.
You proceed.
Yeah. So coming to VisualSim, we have actually built our tool based on these challenges what typical system designers are coming across, and for that actually we have found that graphical modeling and simulation methodology is the best one for identifying or for noticing what exactly is happening in any system itself. So what user can do is, it is something like you're drawing on a blackboard, you can model or you can bring in the library blocks into VisualSim Architect environment, connect them together and configure them with the parameters and run the simulation. It's done. So you can quickly explore your hardware architecture and run simulations with the various set of analysis reports, things like that. So that actually gives you a kind of higher level of confidence over your specifications, what you're arriving at, right? So for that, actually, we provide more than 500 custom and statistical as well as the cycle accurate modeling IP library blocks. And
Okay.
each IP library blocks okay. So yeah, so VisualSim has been used in various applications, and majorly it is used in the area of hardware architecture selection. So as I was telling, it is not about the we call components in the sense it is processors, memories, and bus, DMA, and all those things. We call those as components, and it is not at the level of capacitors and resistors. And we help in selecting which processor will be suitable for my application, whether I should go with Cortex A9 or whether I should go with or Cortex A7 is sufficient enough. I may not have to go for a higher version at all. So such kind of component selection and sizing of your hardware architecture as well. Sizing in the sense whether you need two memory devices on board or only one is sufficient. Whether you need at what speed your devices should run at, and what kind of topology you're going to choose for your design, whether it is ring-based or a point-to-point or something like that, right? So those are the kind of hardware architecture level explorations can be done using VisualSim. Coming to software side, so it is actually used for selecting the scheduling algorithm and how you map your software applications onto the hardware architecture. As I was telling earlier, for example, if there is some image processing things are going on, then you will have to call a DSP or a kind of GPU-based processors, right? So how I should send my data across the board, so how I should define my software behavior flow. So these are the kind of explorations you can do. Which combination or which combination will give you the better performance, things like that. Okay, and coming to networking side, so we actually help in modeling a complete network with the kind of hundreds of nodes that are connected to various switches, routers, things like that, and you can conduct performance analysis at the level itself. When you will be having hundreds of nodes and multiple switches, routers, you can conduct the end-to-end latency and performance and throughput of your specific flow as well. For example, you are sending a data from node 1 to node 10. you're actually going across multiple nodes in between. There are multiple hops in between. For example, if I go from node 1 to, consider your source node is node 1 and your destination node is actually node 10, and to do that you may have to go to node 5 or node 8 in between, which is the nearest nodes you'll be having. So you can perform such kind of complex networking scenarios as well. Right, so that includes your TCP/IP based or UDP/IP based, or even the software-defined networking architecture, which are coming across very in recent days, and cloud-based networks and proprietary network applications as well. So we provide the basic framework to model network architectures and conduct various kinds of analysis on that particular platform to identify whether you're meeting your requirements with respect to performance metrics or with respect to other technology specific requirements as well. Okay?
Okay.
So coming to semiconductors, we help in designing custom IP libraries or IP block itself. For example, you're actually building your own processor. In that case, you don't have to initially, the reason is that, for example, if you design a processor, you'll be keeping in mind that this processor will be used in a specific application area, right? So in that case, you will have to consider whether whatever the processor I'm designing, whether that will suit the requirement of that particular application. So what you can do is you can build up that framework or the hierarchical model of that particular processor in VisualSim and use this as a part of the system which you are going to put it for a specific application area. For example, if you consider you're going to use your processor in the area of networking side, so you will actually you can model the rest of the system with that particular processor and try out all the possible scenarios to see whether that processor that you're going to model is going to work or not. Whether how many pipeline stages you need to have and what kind of instruction set you're going to use, and how many levels of cache hierarchy I should have. So such kind of things you can model early in the design phases itself. Okay?
Okay.
Any questions here?
No questions.
Okay.
I understood.
Okay. So it's actually kind of selecting the right configurations that matches exactly the customer requirements. Okay.
Okay.
Oops. So coming to hardware and software modeling IP library blocks that I was talking about, with respect to the generation of traffic actually models your applications, right? Applications are nothing but sending some data to your hardware architecture. When you click on your camera button, you will actually generate some traffic, and that traffic will be going across your SoC chip in your mobile, and it sends across to the processors and GPUs, things like that, right? So similarly, VisualSim enables you to model such kind of complex traffic scenarios, whether it is a trace file based or a kind of profiler based, and so those traffic reports can be generated. Okay. With respect to reports actually as I told, we are actually in the aspect of like performance analysis and power analysis. Major reports you will be looking at are latency, whether it is end-to-end latency or a kind of device-specific latency. For example, if you are having an FPGA board, you want to know what is the latency in that particular board itself. So that also can be identified, and also the end-to-end latency. At what time you have started your application and what time it has completed its processing thing. Okay, and you can identify the throughput and utilizations of various devices on board, and the average and peak power consumption of various devices, as well as the complete system too. Okay, and with respect to various domains like SoCs and board level and processors, we have a wide set of library blocks, and that can be directly used as a part of your models as well. Okay, what I'm going to do is at this point, I'm going to quickly go into a VisualSim model to just show you a feel about how user will conduct explorations and how they will ultimately get to a specification that meets the requirement. Okay.
Okay.
So I'm going to start off with a very basic example. In this case, as I was explaining earlier, you have a scenario in which you have two CPUs and a DSP core and an I/O block, and that are connected using a bus and a bus bridge. Okay, so the top portion is actually models your hardware architecture, and at the bottom you have two applications that are running. What I'm going to do is I'm going to run simulation. When you run simulations, so as you can see here, we have separated out the hardware architecture as well as the software architecture, right? So when the task arrives at this task 1, it actually virtually maps and virtually sends all the transaction details to my I/O block over here. Okay, so that's the internal intelligence that tool is handling. It actually sends all the details about how much time it is going to take, what is the task size, and what is the destination, and from where it has started. All these details are transferred to this particular I/O block from here. Okay, so we call this as mappers and schedulers. When I run simulation, what we can look for is the end-to-end latency. For in this case, we are looking at application 2, and we can also look for the software task latency for various different tasks too. For example, transferring data or processing the data, things like that. Okay, and also apart from that, we can look for the utilization of various resources on board. In this case, CPU 1 is utilized about 92%. If you look at the left-hand side, and you can see how many number of tasks entered to that particular processor. In this case, about 170 tasks are entered into it, right? And also I can look for my CPU 2 utilization, which is about 55%. Maybe I can send few more applications from CPU 1 to CPU 2 instead of running applications on CPU 1. I can send few more to CPU 2 as well because I have some room over there, right? Similarly, I can look for utilization of various other resources too. Based on this, user will identify whether I'm meeting my requirements or not. What happens if the utilization of the CPU 1 goes beyond 95%, right? So that is the very dangerous scenario that actually tells you that you will have to definitely change your software mapping methodology, how you are sending the data across. Okay? So that gives you an idea about what exactly is happening and whether I'm meeting my requirements or not, right? So what I'm going to do is, as I told earlier, I'll actually over-engineer my design by running my bus at a higher speed. Still, I'm running only 2 applications on this particular platform. If I look at my software task latency again, you can see here earlier there was actually kind of very symmetrical peaks over here, and you can see here now we have few tasks that are having higher task latency, which is beyond 1.5 microseconds. So this is what I was explaining earlier. The bottleneck could be at the bus, bottleneck could be at the processor itself, or in the DSP as well. So this is how user will explore the architecture, define the architecture, things like that. So this is the scenario, or this is the scenario in which user will actually quickly, user can model their projects within few hours, and they can try to identify whether that particular project is feasible or not. Okay?
Okay.
So coming to the next thing, like as I was telling earlier, how user will conduct architecture explorations and how they will freeze up with a specific configuration of the design. So consider this example. This is one multimedia system design. Okay, so here we have the hardware architecture that is having ARM subsystem and an ARM by AXI and SDRAM and a flash that are connected using an ARM by AXI bus. Okay, and at the bottom we are defining the software architecture, which actually gets the data from a sensor. It is actually a camera sensor. It gets the data from there, and it performs read frame, decode frame, video post-processing, rendering, and all those activities one by one. Right? So initially what we are doing is we are actually running all these applications on the ARM core itself, which means you are actually performing everything in the software perspective. Right? So what happens is that when you define, you have considered this as your version 1, and you are running all your applications or all your tasks on your ARM core itself. So I just want to know whether that scenario will work for my requirements. In this case, user is looking for about 13,000 matrices of images being processed for a time frame of about 20 milliseconds or so. And their requirement with respect to power consumption is it should be under 1 watt of power, total power consumption. That's the kind of higher level of requirements. So when we have modeled this particular thing, and if I run the simulation, and I can look for the instantaneous power, the average power consumption of my complete system. You can see here, we are actually meeting our requirement with respect to power consumption, which is actually under 1 watt. Okay, so but yeah, so we are good with respect to power consumption. Now we have to look at the perspective of performance as well. If you look at the performance aspect, we are actually getting only about 6,600 matrices of the image that are being processed in our hardware architecture. We were actually expecting about 13,000 matrices, but we are actually processing only about 6,600. In which it clearly says that you are not meeting your performance requirements at all, right?
Okay.
So what I can do is now I have to look for my hardware architecture.
Can you show me the internal structure of that ARM?
Sure, I will come to that. Once it is, I will explain you the flow, how explorations will be completed. Then I will go inside each blocks and I will show what is there. Is that fine?
Okay.
Okay, so now what I'm going to do is I'm going to run this rotate frame application or rotate frame task on the hardware accelerator. Hardware accelerator, you can consider it as a kind of co-processor. You're running few tasks on a separate processor itself, right? So what I'm going to do is I'm going to send this rotate frame into the hardware accelerator now. Now I just want to see whether this will meet my requirements or not. What you will do, you will again run the simulations to see whether what is actually happening in my architecture. So if you look over here, initially when you start off your simulation, the total power consumption is under 1 watt, but after some time it is gradually started increasing, which clearly tells you that there is something wrong in your system that actually consuming a lot of power. If you consider this particular graph over here, the instantaneous power for hardware engine, that is the hardware accelerator or the coprocessor that we have used, is actually kind of every time it is in the on position itself, which is completely wrong, right? Because we are running only one particular task on that hardware engine, which can't be in on position all the time. Right? For a fraction of second or like for a few milliseconds, you may be running on that that particular hardware engine. But in this case, when you start up your processing, it continuously stays on, and the total power consumption tells you more than 35% is being utilized by hardware engine alone.
Okay.
Okay. So what I have to do is I have to make sure that my hardware engine is will be turned off whenever the task is not coming across, right? So I'll have to write in kind of power gating algorithm to make sure that my hardware engine will be turned off whenever the task is not available, right? So user will again modify the architecture and they will actually turn off that hardware engine once again if it is not being used. So when I run the simulation again, now you have seen that we have actually went from the initial level in which we had only we had a scenario in which you're running everything on the ARM core itself. Then we moved certain application onto the core processor, and we have seen that the total power consumption is huge, and even though we were meeting the requirements with respect to performance. But if you see in this case, we're actually the instantaneous power consumption of my hardware engine is very less now. You can see here there are a very short span of time you will be turning on your hardware engine, then you will quickly turn it off, so that your hardware engine power consumption is very less now, right? Earlier it was more than 35%, now it is under 2%. You can consider that.
Okay.
And my total power consumption of my system is also dramatically reduced and is under 1 watt. And if I look at to my performance perspective, we are getting about 13,200 matrices being processed, which means we have met our requirement with respect to power consumption part as well as with respect to performance perspective. So this is how user will actually go with a kind of step-by-step analysis thing by looking at all the reports what we generate, and based on that they will select their hardware configuration. So at this point they have selected their hardware configuration and their software part as well. Okay, so this part can be sent it across to the next stages. Parameters, system parameters, that enables the user to vary the configurations and identify which configuration is meeting the requirements. And the other part is the components like your processors, memories, controllers, things like that. The third part is your power manager that helps you in identifying the total power consumption of each devices as well as the complete system. And the final thing is generation of reports. Reports are actually not a kind of, you don't have to it is not just utilizations, latency. Apart from that, you can also look for the activities going across your memory controllers, or if it is a networking system, what is happening at each nodes as well. That is also you can generate. Okay.
Okay.
With respect to exploration reports I was talking about, you can look for the application performance and the hardware performance as well. You can see here, this is with respect to your software application that you're running on the platform, and the hardware performance as well. And the power profile means how much power consumption is happening by each devices as well as by the whole system. Oops. Okay. So this is a kind of differences with the current modeling technologies. And VisualSim, as I told, it is actually helps you in modeling end-to-end system modeling. That includes your networking systems, hardware and software parts too. Okay, and helps you in evaluating the total power consumptions, latency and throughput and utilizations. If you compare VisualSim with MATLAB, MATLAB actually works only in the sense of correctness of the math or the algorithm what you're implementing it. And Simulink is actually more of a kind of optimization of your control algorithms and things like that. And it doesn't do any performance analysis, things like that. If you look at the lab view, which many of the people look it as a kind of competitor, but LabVIEW is actually more of a kind of implementation of your control systems, and it actually doesn't provide you libraries in the area of processors, memories, and things like that. Okay?
Okay.
And to wrap up the session, VisualSim is actually a kind of, it takes very less time to learn the tool, so that the initial learning curve is very short. And as we provide many application templates, the model development time is very short. And for example, if you have kind of higher picture about your architecture and you are missing something about your memory arbitration algorithms or something like that, you can keep those things as a kind of higher architecture level or a kind of very higher abstraction level, and you can start off with other subsystems too. You don't have to have complete details about your architecture to start off with the modeling thing. You can start with subsystem level and then you can leverage it to the complete system level. Okay.